Everything's fine. Great. Yeah, so first of all, the reasons, we've heard a lot about that. And in fact, just in the last answer, we got exactly this case, but obviously not for a Ferrari, but for washing. It's the end-to-end case, yeah? So complex requirements need deeper and also, I would say, semantic data models. Because, if you want to go from one step to the next step, let's say, what is the design of the part to make this product better? But then the part is made out of another component, and the component is made out of a material and a formulation and so on. So how can you then really know what are all the things that play together to address a highly dimensional space? So this is obviously addressed partly with things like machine learning, but also you need to actually trace and track all of the entities that play a role along this process, which we have seen also the example. And this is really to support the translation at the enterprise level. Yeah, translation, what we want to achieve through doing this is to go from the individual hero, yeah, the person that says, I have the answer, to a systematic innovation management at enterprise level, which involves more than just departmental knowledge or individual knowledge. So these bullet points that are also shown here, then these bullet points here, they are really bullet points taken from a description by IBM of knowledge management systems, and they really reflect what we need here. Yeah, what is the enterprise knowledge? How can we maintain it? How can we combine diverse content in connected data sources? Find relevant information more quickly, more transparency, better informed decisions, and uncover insights. So it is in the end about better informed decisions. And the pyramid that in the OntoTrans and in many other initiatives is put together and integrated is the one shown on the right, where you have multiple data sources and knowledge sources. So here we are bringing together, for example, as we've seen already, experimentation, existing data, simulation, and then we document the data. But before we can really make decisions, we have to have the sense making in the layer in between. The data in themselves are not enough meaningful, at least not if you go to the enterprise level and go beyond the individual who knows exactly what the data are. So going up this pyramid for the improved decision making is what we're all about. Now, the systems that enable that are very much the semantic knowledge management systems. And this was, from a public open presentation given by Siemens, just as an example, how in a company knowledge graphs have been moving forward by generations, integrating more and more functionalities in the company to provide this type of integration and decision making that we've been talking about, and also integrate deep learning and so on as well. So this is all about semantic data management. So what is it? I mean, it's surely familiar to many of us here, but again, as a reminder, it's really applying semantic web technologies to the management of data. Yeah? And the benefit, this is taken from Cambridge Semantics here, is a flexible interconnected data model. This is what we're working with to save time, cost, and improve maintainability over traditional technologies such as databases. And the one point is always very important to remember: this uses what is called the open world assumption. Yeah? This is part of the semantic data management, that we don't know all the facts, we don't cannot construct the relational database, which is then a closed system. And so if we don't know that, new facts arise, this is much easier in these types of systems. These technologies underlie the web and the semantic web. I like also this diagram from Devopedia. You had all of the connections in the web already, but all of the connections, then all of these nodes then also have meaning. Yeah, so they are labeled like persons or buildings or other information, computational information, and so on. So when does it really make sense to do that? As we said, it's when new factors emerge. So the data can change constantly. The views on the data may change. Collaboration takes place. Heterogeneous data sources are required. And also there is a lack of standards. If I have already very good standards, then it's easier to know exactly that's what I need to represent and nothing else, and how I represent it. But the semantics can provide that layer of classification and interoperability if I don't have already a fixed syntactic standard. And the benefits are very widely documented. So reducing the cycle time of accessing ready-to-use data, and typically this is 30% introduction in the time for integration design, 30% reduction in deployment, 70% reduction in maintenance relative to traditional data methods. The other is, I mean, this is now again very much at the top of the discussion agenda as the market research organization Gartner puts these knowledge graphs as one of the top technologies and tracks their evolution. We've seen this also before. There has been, for example, here this understanding the role of the data fabric, which will come in a minute. Publication, some new publications on that recently, and then on LinkedIn, we also find people that companies like Chris Brockman, the CEO of Accenture, which is a semantic knowledge management company in Germany, that also mentioned that there is another benefit. A big benefit is the power from the ability to reason on the semantically integrated data. And according to their customers, that outweighs even these very large data integration insights by 10 to 1 for customers like Siemens, Bosch, Nokia, AstraZeneca, who are their customers. So again, we see multiple layers of benefits arising as a result of these systems. Examples, this is from Accenture, is, for example, product management system. So product management often relies on specification of different components, and sometimes you have legacy systems where you don't know, is this component fit for this purpose? And so by building a product management system with the over 500,000 components, they reduced search time by 98%. Everything is self-service, it's completely scalable. Other example we discussed a little bit here, unfortunately, our external advisory board member from Springer isn't here today, but we know also we work in the OntoTrans project with Stardock as a partner, and Stardock has been working with Springer materials to integrate a very diverse range of databases they have from legacy, different systems across different materials, across different disciplines. And this knowledge graph now contains 100 million triples spanning data sources like the Landau-Bernstein Springer handbooks, relational databases from corrosion to polymers. So with that, they can uncover complex relationships from simple keywords. And if you go to materials.springer.com, you can, even without a license, you can try and see some of these types of searches here that this system enables. Another buzzword that is around at the moment in this field is data fabric, and I kind of like this fabric because the fabric looks a little bit like the fabric looks a little bit like like a net, like the ontology that is connecting everything together. So, and in fact, this is a way of integrating different otherwise unconnected data into a system where that can be queried as one. And in fact, the under the hood of these of all of these knowledge graphs is, of course, well, first of all, under the hood of the data fabric is the knowledge graph, and there that is driven by an ontology as well. So a famous example of knowledge graph is DBpedia, which has been a project in Germany, started, I can't remember, 2000, well, maybe close to 15 years ago or so, something like that. So it's it takes the information from the Wikimedia projects and uses an ontology consisting of 320 classes, 1,650 different properties to provide, a very searchable, very nice interface into a very wide range of data. One note about the things I want to say still to come is also that it has a lot of classes that are also from what is called schema.org, which is a system from Google. And nearest to what we are doing, it has something called a chemical substance. But it's also of note that it has no classes really about materials. And if you look at all of these things like linked data, DBpedia, and so on, they actually lack really materials information, despite the fact that surely this information is out there. And I would also argue that's because there is actually a lack of an integration of schema and ontologies from the materials field that are available and integrated in this field. So why ontology-based materials acknowledgement is all of these points that I already said, but maybe I will kind of skip a little bit to go a bit faster. The question is, we need to have, or the point I want to make is to move the field forward. We have a lot of the ingredients. Yeah, we know we're doing it in the OntoTrans project, but I think on a more global scale also we can do more with things that can be quite impactful and beneficial to a very large community. So it's really the foundations that we need. And from other fields, for example, if you look at chemistry, the terminologies are defined in the IUPAC. At least some of the classes find themselves in schema.org. So there is an ontology called the Kebi ontology, and whether one likes the Kebi or not is another question. But it is has made a big advance in bringing together the field and really curating data around that. And what is the status in material science is really that there's a very heterogeneous terminology, and looking at the challenges of interoperability as formulated by the European Open Science Cloud, there are two challenges which 100% are challenges for materials, which is the lack of common explicit definitions about the terms that are used by user communities and the lacking common semantic artifacts across communities. Yeah. We also had or have been investigating this field in the OntoTrans as well as OntoCommons projects with a number of people. Some of them are actually here, like Ilaria and Manuel and Jesper and so on. We are putting together a review of and alignment of domain level ontologies for material science. This was basically looking, okay, what are the ontologies out there that could drive these systems? So we found about 50 machine readable ontologies. They use different top-level ontologies, SIO, MO, BFO, SUMO. And then we also looked, okay, how much do they cover terminologies in materials? So we put together a glossary of about 700 terms. From textbooks, from other sources, like the demonstrators, characterization and modeling, Zen workshops. Yeah, so we arrived at a total of about 800, and we classified them into different subject areas, like types of materials classes, material structures, materials properties, and so on. And then we analyzed automatically, as well as by expert analysis, the ontologies, and we see that in some areas in chemistry, we have up to 35% of a certain discipline covered in the ontology. In most cases, it's like very few percent. Yeah, so the domain terminology coverage in ontologies in the field is actually very low. We also looked at what are the most frequent terms. So obviously, we find material, atom, structure, component, property, and so on. So what we then decided is that we use an approach developed in the OntoCommons project called the bridge concept, meaning a very rich semantic description of concepts so that they can be widely used in building ontologies, bridging between ontologies, and so on. So these are matter, material, atom, molecule, substance, physical quantity, materials property, materials processing. And so by developing those, we want to actually, let's say, also lay the seeds for more coherent description in the field, and working, of course, with the MO ontology further to do that. An example, and Emanuele showed, of course, how this is all derived as well, is if you look at materials in chemistry. So if you look at physical matter and material and chemical substance, we should have, like, physical matter is very general. Material is something a bit more specific. For example, a material is not a single atom, which is a molecular entity, but a chemical substance is defined as a material with a specified chemical composition, and we don't necessarily know what the chemical composition even is of a material. But if you look at schema.org and the use of the term in like Wikipedia and so on, because chemical substance is the only term available, materials are, you find materials as subclasses of chemical substance, which logically they are not. So we should have a better way of doing this, and this is also then addressing further materials classes and how you divide them by mesoscopic and continuum, by states of matter, like solid, liquid, gas, by different types of functional defined, size defined, chemistry defined, structure defined materials. So overall, coming more with a community agreement on high level concepts and classes that will help driving knowledge management forward in a semantic way in materials. So I want to conclude saying that semantic data management brings a wide range of benefits, and they are in particular relevant to research environment where we need an open world assumption. And there's very many benefits I showed, and we have seen today the underlying knowledge graph. So they need to be based on a well-developed fit-for-purpose ontology. There are many knowledge graphs and ontologies in different disciplines, but a severe lack in the materials area. So that we don't have really the benefits of some of these even public tools like Wikipedia that we could have in the field. Now with EMO, we have a solid basis for that, and with OntoTrans also a system that can make use of that. So we can realize the semantic web vision for materials innovation, which was really the vision of Tim Berners-Lee, and here he is with what he said about it, and also the semantic data about him, which is kind of closes the loop. So thank you very much for that, for your attention. Here's an acknowledgement of the co-workers and also the funding for these projects. Thank you.
Thanks, Gerhard.